Okay. Should we? I think we should probably just get started now. So this is, I think, the fourth lecture in the summer series. My name is Andy Derbyshire. I'm a staff scientist in the functional MRI facility, and this is the talk on supposedly advanced MRI and fMRI acquisition methods. And so it's basically a somewhat of a, it follows on really from Vinay's talk if you were here on Wednesday. And so it basically continues on with that. And I'll cover a lot, some of the material will overlap a lot with his, but that's because I have to basically build up the same kind of framework. So I think it doesn't do any harm to revisit some of that. So we'll have a quick review of the basic physics underpinning MRI, which is NMR, nuclear magnetic resonance. And then we'll talk about some of the MRI imaging tools and techniques, and I'll zip through those pretty fast. And then we'll get into sort of discussion of what we call case-based trajectories, which is really the imaging methods, and move on to image acceleration, and then techniques for manipulating image contrast. Okay, so NMR is the phenomenon which underpins MRI. And it's basically due to we're looking at the phenomenon associated with the nucleus of the atom, and in particular hydrogen atoms, which is typically the nucleus we're looking at, which is good because there's two of them in every water molecule. Okay, and in the presence of an external magnetic field, the nuclei can absorb and emit electromagnetic radiation. And the way they do that provides information about the environment those water molecules are actually experiencing. Okay. There's not a lot of maths in this talk. In fact, probably the most useful equation, if you're going to take one away from here, is that omega equals gamma b. And here, omega is the angular frequency, so it's 2 pi nu, nu is the absolute frequency. Gamma is the so-called gyromagnetic ratio, also sometimes referred to as the magneto-gyric ratio, but it's basically the same thing. And B is the magnetic field strength. Okay, so omega equals gamma B, and here we're going to be basically talking about protons. So there's actually only a single gamma here, which is 42 megahertz for every Tesla. So Tesla is the unit of how much magnetic field we have. And so we can, one way to think about this is that if we have a bunch of, an ensemble of molecules, we can think of them collectively as having a sort of magnetic moment, and with an associated spin, that will be aligned with the magnetic field. So we have this vector m, which is initially aligned with the magnetic field, which we assume is along the z direction. And so we have m is 0, 0, m naught, which is just the resting magnetization. Okay? And this is technically exactly how big that is when it's fully relaxed. Okay? So looking at this, typically MRI scanners, at least the ones that are used for human imaging, are at either 1.5T or 3T in clinical settings, and just recently 7 Tesla scanning has now been approved. We've had a 7 Tesla scanner here for about 10 years now, and so because omega equals gamma b, these have associated frequencies of about 64 megahertz, 128 megahertz, or nearly 300 megahertz. Okay, the fMRI facility has 4 scanners, which are 3 Tesla, and 1 scanner that's a 7 Tesla. Okay. So in the lab frame at equilibrium, the magnetization's basically pointing along the direction of the main magnetic field, and we can kind of think of it as being like a rotating vector. So if we were somehow able to tip this magnetization away from the main magnetic field at some small angle, what would happen is it would then precess around this. It would still rotate, but it would precess around the main magnetic field B naught at omega equals gamma b. Okay. Now it's a bit inconvenient to deal with that because it's basically spinning and it makes the equations complicated. But so we work in a rotating frame, and we just imagine our frame is rotating around, so we can sort of freeze the magnetization if you like. So we don't get that. We take out that rotational factor. And so we work in a frame of reference that's also rotating at ohm equals gamma b, and then the magnetization just appears to be frozen at a small angle offset. So in the rotating frame, if we now imagine we're working in this rotating frame, if we somehow can apply an additional magnetic field, B1, that's perpendicular to the original B0 field, and bear in mind this looks like it's still, but it's in a rotating frame, so this B1 is itself rotating in our magnet. So then we have a new magnetic field present. And what will happen is, because omega equals gamma b again, the magnetization rotates in towards this, what we call the transverse plane, which is the xy plane. Okay. Feel free to stop me if any of this stuff is, if you've got any questions. Okay, so this is how we can tip the magnetization away from Z. We can apply a B1 field along either the X direction or the Y direction, and then the magnetization will tip away from Z towards Y. Actually, if we just apply it for a short time, it'll tip, and then we can just leave it there, and it'll return to that. It'll stay in that position. Okay, and we call the angle it's excited by the flip angle. And so by applying either more B1 or the same B1 for a longer time, we can change that flip angle to be anything from 0 up to 90 or even beyond to 180 degrees and further around. So basically we apply a B1 magnetic field along the rotating frame x-axis. The magnetization rotates towards the y-axis, and then we turn it off and we obtain the flip angle we want. Okay. Now the component of magnetization that remains along the z-axis is known as the longitudinal component, and the magnetization that's in the xy plane is referred to as a transverse component. And this is important because the transverse component is related to the amount of signal you see. You don't pick up any MRI signals from the longitudinal component, you only receive signals from the MXY components, and that's why every MRI pulse sequence starts out with an RF pulse to flip magnetization over. Okay, so basically the signal is proportional to what we call MXY, and it's convenient to write this as a complex number, MX plus IMY, and you can think of the XY plane as being essentially like a complex number plane, if you like, and that's a convenient way to think about the signal that's induced in the receiver coil. Okay, so having excited the magnetization then over time recovers back to its initial state, and it does it by there's two important mechanisms by way this occurs. One is T1 relaxation, which is basically how the longitudinal component recovers. And it recovers according to a pretty simple differential equation like this, which is called the Bloch equation. And when you solve that equation, it basically amounts to the fact that if you start with all your magnetization in the transverse plane, it recovers over time, asymptotically reaching the original M0 amount of magnetization, which is fully relaxed. Okay. And so here's another picture of that happening, but you can see the magnetization has been fully excited into the transverse plane, and then over time it recovers, and the MZ component goes longer and longer until it fully recovers here. Okay. So the other effect, the other relaxation method is the way that the MXY component returns back to equilibrium, which is essentially 0. And this is important because this is how your signal decays. Once we've excited it, as I mentioned before, the signal is proportional to the transverse component, and that signal will then decay by a mechanism known as T2. And so that basically decays by a straightforward exponential decay. So we start out with, after the initial excitation with magnetization, with some transverse magnetization, and that just dies away by T2, and that basically causes our signals to go away. Okay. In practice, we don't even manage to get the T2 amount of time for us to record our signal, because there's other spin dephasing. Imagine we have a sort of blob of water. They all experience slightly different magnetic fields, and they gradually become out of phase with one another, and so the signal actually decays a little way faster than that due to T2 star relaxation, which might seem kind of annoying, but actually it's quite important because that's the source of our, what that will turn out to be the source of our bold contrast that we'll use for functional imaging. Okay, one more technique I just wanted to introduce at this point is something called the spin echo, which you may hear of, which is a technique where if you initially excite the magnetization with a 90-degree pulse, and as I said before, the spins will decay by T2, but they'll also decay faster because of the T2 star, the dephasing effect. If we then apply a 180-degree pulse, essentially all those spins flip. Okay, all those spins will flip around, and then instead of dephasing, they will rephase, and they'll form something called a spin echo. And the magnetization will basically all come back together, and we'll get a sudden recovery of the signal back to the ideal T2 decay rate. Okay, so now moving on to imaging. So that's what we've talked about so far is what happens if you just deal with magnetization as a bulk signal. Right? There's no spatial discrimination between what's going on. So the way we induce some spatial variation so we can identify where things are coming from, this is the most important part in imaging, is to understand where the signals are coming from in space. We use magnetic field gradients to do that. So a magnetic field gradient is basically, the MRI image formation is based on, again, omega equals gamma b, which, so basically, supposing we can make a spatial magnetic field gradient. So in 3 dimensions, this would be gx, gy, gz. It's a vector quantity. So gx is let's say we consider gx. It's how the magnetic field varies in the scanner in the x direction, which we take, if you imagine the bore as being the round bore, is the sort of side to side, left to right part of the scanner. And if we put a gradient in gx on, it would be like saying, basically making the field a little bit stronger on the right and a little bit less strong on the left. Okay? And you can think of this if you imagine being the scanner from being on the left side of the scanner to the right side of the scanner, being reduced magnetic field over here and increased magnetic field over here, because this gradient line is superimposed on the main magnetic field of the scanner. Okay? So typically gradient fields, you might use for imaging might be something like 30 millitesla per meter. So at 10 centimeters either side of the center of the scanner, you have about 3 millitesla. So it's about 1,000 times smaller than the main magnetic field. Okay, so so if you can imagine this is your main magnet here, these large blue bars, then with the main B0 field and the gradient superimposed, you'd have, if you put an X gradient on, you'd have a smaller reduced magnetic field on the left and increased one on the right. Okay, and so because omega equals gamma b, what this means is that spins on the left, any spins that, in your body that are on the left side of your body would be spinning at a slightly reduced frequency, and the ones on the right are spinning with slightly increased frequency. And of course, we can control these gradients. They're not like the main field of the magnet, where it's basically on all the time. We can control these magnetic fields, and we can turn them on. We can flip them over, turn them off. So you can switch the magnetic field from being from left to right to left. Okay. And we can also make it so that the magnetic field's in the z direction, which is like through the magnet, or indeed up and down in the magnet. So it's a genuinely vector quantity. We can have a magnetic field that's from left to right, right to left, or up and down in the magnet. Or we can have some combination of all 3 directions. Okay. So let's say there's a slice that we want to excite in our scanner. If we turn a magnetic field gradient on, the resonant frequency of the spins through, actually my head here, will vary. The resonant frequency will vary throughout from neck through to the top of my head. And there'll be a specific frequency associated with this point here. And there's a group of frequencies associated with a band here, with the thickness, depending on the thickness of the band, there's a sort of group of frequencies. Right? So if we excite with that, with a combination of frequencies corresponding to that band, we'll end up with an RF pulse that looks like this. This is our excitation pulse. And then we'll excite only spins inside this band, because this is a resonance phenomenon. So things that are, if we use frequencies that are not the exact frequency of the spins we want, they pretty much ignore them. So basically, if we use a group of frequencies, a pulse with the exact frequency band matching where we want to scan in space, depending on the magnetic field gradient we've applied, we can excite spins just in that narrow slice. Okay? And so having done that, that means we can just basically selectively excite. That's one way which we can selectively discriminate between different parts of the body to make images. Okay. So again, here's the sync pulse. This is what a pulse looks like. It's got a narrow band of images frequencies in it. And then when you use this to excite magnetization, you end up with MXY signal that looks like this. And then you can apply an additional gradient and you can bring it back. And so you end up with all the signal in basically in MY. And the corresponding MZ is now just like a notch, because we've basically used up all the magnetization from this notch. And over time, this MZ will recover by T1, and this magnetization will decay by T2 and T2 star. Okay, so having excited the magnetization, then what can we do with it? So we've got this plane of magnetization we've excited, and now we'd like to make further encoding of magnetization to try and work out where the signals are all coming from. And we can use gradients to do that again. So we've got this, there's a technique called a gradient echo, where we basically, if we put a gradient on, all the spins in that excited slice will now process with slightly either increased frequency or reduced frequency. They're the only spins in the transverse plane, so that's where all the signals are coming from. And so what we can do is we can record the signal that we hear, because we get all the signals from this transverse plane. And we get a combination of low frequencies and high frequencies. And when we look at those signals, we can use something called a Fourier transform to sort the amount of each frequency present. And that'll tell you if there's more signal on the left or more signal on the right. Okay? So generalizing this, we can see that the magnetic field, the effective magnetic field gradient, is that we have a superimposed field on top of the main magnetic field. We have this gradient field and superimposed, and the strength of that magnetic field is G dot R. That's the additional magnetic field. And so therefore we end up with an additional frequency, omega, which is gamma G dot R, should be gamma in here. And we can use that to sort of encode the spatial position into the magnetization. So let's suppose we have consider a small blob of tissue somewhere inside here, somewhere around here. We can put on a magnetic field along X or a magnetic field along Y, or some combination, and then we end up with an additional frequency. Delta omega is G dot R, gamma G dot R, as I said before. So over time, this accumulates phase. We just integrate it with respect to time, and we end up with some accumulated phase. And then if we consider that over the entire object, we can now integrate across the, we can integrate the additional phase across the entire volume, and we end up with a signal which is like this somewhat complicated looking equation. But if we write k as gamma over 2 pi integral gradient with respect to time, this simplifies a little bit into a sort of fairly familiar pattern. That we have the signal of k is proportional to this, is equal to this formula here, which is basically a three-dimensional Fourier transform, or maybe a two-dimensional Fourier transform if you're doing 2D imaging, which we know how to invert, so we can get back the actual amount of signal from each location in space, because this is just basically a Fourier transform. So the signal is a Fourier transform of the object, and this is the signal we collect in k-space, and the object is a Fourier transform of the signal, the inverse Fourier transform of the signal. Okay, and I think Vinay showed you the same pictures here yesterday. So this would be the a picture. This is its Fourier transform. The center part of the image is the low spatial frequencies. The edges are the high spatial frequencies. So point near the center of K-space can be represented as a low spatial frequency like this. Point at the very edge of K-space has a very high spatial frequency. At the center of K-space, there's no phase across the image is another way of thinking about it. As we step through K-space, we gradually increase the amount of phase across the image. You can see by these green bars down here. And correspondingly in the other direction as well. So in order to make an image, we basically have to sample the whole of K-space. When we first excite, we can consider ourselves to be at the center of K-space. So K of t is the sampling position. And because K of t is the integral of the gradient with respect to time, that's kind of like a motion type of equation, because we can imagine ourselves as basically sampling at our K of t position. And we can think of G of t, the gradient vector, as being our speed. So if we turn a gradient on, in the x direction, we'll move this way. If we turn a gradient on in the y direction, we'll move this way. And we can control how fast we're traveling by varying g. G is basically the velocity through K-space. Okay? And then we take samples as we go. The small step sampling size, the step spacing, determines the field of view. It's a reciprocal of the field of view. So bigger steps mean smaller field of view, smaller steps mean wider field of view. And the entirety of, the distance across the space we require determines the pixel size. Okay, so here's our gradient echo example again. So what's happening with that gradient echo example I started with as a motivation is we have the RF pulse to excite us into a transverse plane. We have what's called a dephasing gradient, which takes us to the edge of K-space on the left. Then we have a readout gradient, this gradient here, which then drives us across K-space, sampling as we go, and we collect these samples all uniformly spaced. And that's our data. And if we take the Fourier transform of that, we end up with a profile to our object. Okay, we can do a similar thing in the phase encode direction. And so here I've got a kind of this isn't a real sequence, but it's basically showing multiple steps of a phase encode gradient. So the imagination is that you take you excite, and then you can just offset and collect single samples at each one. If you combine those two, what you can imagine is a slightly complex looking sequence here. But if we take it apart, we've got an RF pulse here that's slice selective. So that gets us our slice. We have a gradient echo in the read direction here, so that drives us to the edge of K-space, and then we read out. And we've got these offsets in the phase encode directions, which means that we basically, on our first scan, we'd go to this edge of K-space and read out. And then on the second scan, we go to the next line up and read out. So that's what this stepped gradient means. So we basically repeat the scan over and over, collecting one line at a time until we sample the whole of K-space. And then we can make our image. Okay, and that's the way the vast majority of MRI scans work, actually using this. This was called Cartesian sampling in 2 dimensions. Okay, but of course, we'd like to go a little bit faster than that, because we want this kind of scan takes maybe like 10 seconds to several minutes to acquire. Okay, we'd like to go quite a lot faster than that. So remembering that the equation is that we can control the position in K-space by manipulating the gradient, because the gradient's the velocity in K-space. What happens if we start in the middle, go to the edge, read out a line, flip the gradient over, and go the other way, and just keep doing that backwards and forwards, and blipping up at each, just having a little blip in the y direction to move us up to the next raster line. So that's what this sequence does here. We have the excitation here, slice selective excitation. We have an initial offset in both kx and ky, which are these two gradients here. and then we flip those gradients over and read out this first lobe. This first big lobe takes us from left to right. The next lobe takes us from right to left. But in between we have a small blip which pushes us up to the next line. So we can just read out one after the other until we acquire the whole of K-space in a single go. And this is the echoplanar imaging method, which is the one that's mostly used for functional imaging and bold imaging. Okay, so this is pretty much the fastest conventional acquisition method there is. It basically acquires the entire scan after a single excitation. Okay, and the limits on what you can acquire with this are basically that the whole time you've just got this one excitation. So the signal's dying away by T2 star decay the whole time. And so basically you need to be able to collect the whole image before the signal's gone. Okay, so that limits basically how far you can go, because it depends on the strength of your gradients as to how big this region can be, right? And as I said, the extent of this region that you sample determines the pixel size. So that ultimately sort of affects the resolution of your image. Okay, so generalizing what we just said, we can basically acquire other trajectories as well, similar to what we did before. You can imagine this was an early echoplanar method, had this sort of sawtooth type of acquisition. There's some people who like to do spiral scans. You can imagine a scan something like this one if you had sort of sinusoidal gradients at different frequencies. And so there's basically as many different trajectories as you can dream up, because you can do anything, anything that your gradients can physically allow you to do within the limits of the hardware. You can devise a trajectory to do that. Okay, so that's a sort of recap of the image acquisition, the basic image acquisition process. So now I'd like to move on to accelerating the acquisition. As I said before, the conventional acquisition is limited basically by the gradient performance, right? That affects how far you can cover in K-space in a single readout, or in the available imaging time. So you end up having to repeat the scans over and over to fill in more and more regions of K-space, and that leads to long acquisition times. And the alternative is to have lower temporal resolution, reduced coverage, and so forth. So what's the alternative? Well, there are some, in the last 20 years or so, there's been some developments for accelerating the acquisition process. Okay, so the first one, which is really not really all that smart, is to basically just acquire a small chunk in the center of K-space. And that way you can speed up the imaging process. But the problem is that you end up only collecting the low spatial frequencies, and you end up with a significantly blurred image. So I think we'll just dispatch that one pretty quickly. Another method is to notice that in K-space, according to the mathematics of K-space, basically if your underlying object is a real valued object, so and we think it, most of our objects are real, so you can make the simplification that the conjugate point in K-space, so if this is our center of our K-space, and we to consider a sample down here, the conjugate point, which is at minus kx minus ky, is the complex conjugate of the original point. So if we only acquire some subset of the data, we can then synthesize the missing block from the data on this side. And so we can either do that to shorten the readouts and do all the phase encodes and shorten the readouts, or reduce the number of phase encode lines, but keep the readouts the same length. But it's either or. You can't really do both, because then you'll end up with a section that's kind of missing, but you can't synthesize. Okay. Okay, so that's a pretty old method as well, actually. But these are known as partial echo or partial necks. These type methods. So there's partial echoes which are used to get short TEs because your readout time is much shorter. Or partial necks means less phase encode steps. And these date back from fairly much to the fairly early days of imaging. The other methods which have become popular are methods called parallel imaging, and these are based around the fact that modern MRI systems now collect data from a large number of RF coils that was placed around the head. So back in the very earliest days of MRI imaging, the coils were basically, the receiver coils that you put your head into was really just one single channel, one coil device. So all the signals were all coming through, and they would come out on one cable, and it's all just one composite element, if you like, to pick up the sensor element. In a modern scanner, we typically have 32 or 64 channels. Sometimes less, but that's a pretty normal number now to have 32 channel or 64 channel array coils. I'm showing just 6 here. And these are much smaller coil elements positioned around the brain. And one of the benefits of doing this is that you basically can make a separate image for each coil, and then you can combine them in. Originally, the idea was that you could take these images from each coil and combine them in and get an improvement in SNR, because you can combine them in a more optimal way. But then someone realized that you can, but if you look at this image here, this is what a coil down on the bottom right would see. And you can see it's much more sensitive to signals from the bottom right because they're much nearer. And these would be the sort of imaginary field lines that would be emanating from that coil. Now, we don't transmit with that coil, but there's a reciprocity. So this coil sensitivity, if you imagine a loop of wire and you imagine the field associated with a loop of wire, when you're receiving, there's a reciprocity between transmit and receive. So basically, it's it helps you imagine what the coil profile would look like. So basically, if you've got a coil, it's much more sensitive near the coil than it is far away from the coil. So if we consider this coil element here is sensitive down here, and if we had another coil element up here, it would be sensitive up here. And of course, we've got them all around the brain, right? So if we have that, if we have these coil profiles and we know what they are, if we measure what they are ahead of time, it means we have additional information to help us do spatial localization. So returning to this idea of K-space, remember we said that the intersample spacing is dependent on the field of view. Okay, so if we make the samples closer together, we have a bigger field of view, and if we make the sample spacings further apart, we have a smaller field of view. So the upshot of that is if we drop half our samples, okay, now we'll have basically half the field of view we had originally. Okay, and what that looks like is that if we what that looks like is that we now no longer have enough KY field, y direction field of view to actually fully contain our image. And what happens is the image wraps around, it aliases back into our field of view. So the top part, you can see that in the middle we do a good job, but at the top, where the image goes off the top, it actually comes back on at the bottom because it wraps around, and where it goes off, where it's missing at the bottom, it comes back on at the top. And so that means if we consider a point in the image here, it's no longer, that point in the image is no longer representing a single point in space. It's actually a combination of a point like at the top part of the image and from the bottom part of the image, added together in a linear combination. And that linear combination is dependent on the coil profile that we saw before. So if we look at the coil 1, for example, it's bright at the bottom and it's dark at the top. So in this image, this should be dark at the top and bright at the bottom. So there's a big contribution from the bottom. This blob here, when we make an image from the coil 1 image, it's got a big contribution from the bottom part of our object and a small contribution from the top part of our object. And correspondingly from coil 2, it's the other way around. And so if we imagine that there's one true object underneath all this, the IXY, what we end up with is a kind of set of linear equations here. This is basically a set of linear simultaneous equations. And I've shown it for 2 coils, but in practice you'd set up a set for 32 channels, because we have 32 channels. So you set up this linear simultaneous equation set for 32 channels. And you can write it in a matrix form, which is much easier. And then you can solve that using basic linear algebra, and you can solve it for the image. And basically, so what you've done by doing that now is you've managed to acquire the same image you originally would have had but with half the number of sample lines because we doubled the field, we doubled the step. So that's given you an acceleration factor of 2. Okay, and we can do this for higher acceleration factors by eliminating more and more lines and increasing that sample spacing. And basically, you can do this for rates up to about 4 or 5 before you start running into problems because these matrices become ill-conditioned and they're not, they don't invert well, and then they end up amplifying the noise in your image. But you can get pretty good, typically you can get pretty good accelerations up to about 3 or 4, maybe 5 with this. Okay, so this analysis this kind of method is called parallel imaging because basically you're using all these receiver coils in parallel to make separate images, and then you're recombining them, and so you're basically doing. The idea is that you're acquiring data in parallel to do this. Okay, and all the image reconstruction was done in the image domain. We made these sort of overlapping images, and then we solved the simultaneous equations. But there's this reciprocity between image space and case space. So there are also methods of parallel imaging where the math is all done in the case space domain. And so again, here's our undersampled case space where we've eliminated all the half the lines. And what the idea here is that you can synthesize the missing data in your imaging data set by looking at the neighboring points. So if you consider the neighboring points from all the different coil data we have, so we have these 64 or 32 channels, and so we have case spaces for each of those. You can imagine synthesizing missing data by considering all those channels simultaneously and figuring out how they combine to give you the missing data here, because there's basically there's redundancy in the data because of the large number of coils we have. And so the math is basically it's a little harder to write out for a presentation, but you can basically synthesize all these missing samples. Now, as I said, in the sense case, in order to solve the problem, we needed to know what the coil profiles looked like in space for each of those receiver coils, right? So we needed to know what the B1 field would look like from each of those coils. So we have to actually measure that ahead of time. And again, in Grappa, essentially the same problem, but in the other domain, we have to understand how to synthesize these data. So we need to basically take additional calibration data in order to perform the reconstructions. So this means that before we start collecting data, right at the beginning of the scan, typically, we will collect additional data in order to sort of help us solve the image reconstruction problem later on. Okay. So moving on from parallel imaging, or maybe perhaps this is could be considered to be yet another case of parallel imaging, is a technique known as multiband or simultaneous multi-slice imaging. In this case, we basically, rather than trying to do something during the image encoding process, what we do is we excite multiple slices simultaneously. So before, when we wanted to just excite a single slice, we used a sort of a group of frequencies centered at a center frequency. And that band would excite a narrow slice within our object or our subject. So if we generalize that, we can now imagine a situation where we acquire multiple slices by having several groups all superimposed. So you just take the RF pulses and combine them all together with a particular frequency modulation. So we've got basically, and you excite multiple bands because it's a resonance method. Okay, so when we do that, we basically apply this RF pulse, and it now excites 4 slices instead of 1. And then we do, and that's in the through plane direction. And then we use, having excited all those slices at the same time, we just use our regular imaging method to make images. Okay, and so what we end up with is we have these 4 excited slices, and then we have a corresponding point in the image. Now we're only doing our imaging in X and Y, so if you imagine the through-plane direction is Z, then when we do our imaging, we're only discriminating according to the X and Y position, and we end up with a sort of superposition of all the slices, which looks like a kind of mess, right? Because it's all just piled on top of each other. Okay. But once again, because if we know the coil profiles, there'll be a different for each coil. There'll be a different there'll be a different sort of weighting factor for there'll be a different weighting factor for each of these points within the volume for each coil. And so you can set up 32 or 64 simultaneous equations, and it's just like the sense method I mentioned before, and you can basically solve that system of simultaneous equations and separate out all these slices. And again, the same limitations apply. You basically you need there to be enough variation between the different coil elements in order to be able to invert that matrix in a sensible way. Okay. Something you can do to help that invertibility is you can apply tricks during the image acquisition process to stagger the images so they're not actually acquired directly one on top of the other, which increases the separation between the corresponding samples and improves the invertibility of that matrix. And this is a method known as caipirinha or caipi. So you'll often hear people talk about caipirinha during image acquisition. Okay, so those are really the main methods for applying image acceleration. Okay, so now I'd like to move on to talking about the image contrast. Because so far, basically, I've talked about how you make an image, but you kind of get the image that you get when you use those methods, right? And there's some intrinsic contrast to the pulse sequence because you excite the magnetization and then you collect this imaging data, and while you're collecting it, the signal is decaying by T2 star, and so there's some intrinsic contrast built into the image due to the imaging pulse sequence we use, but it's difficult to really manipulate it or control it in a subtle way, because it's basically kind of built in that if you acquire an image with a gradient echo, it's going to kind of look like this, and you can adjust it a little bit, but not a huge amount. So one method of manipulating the signal of the image contrast is to use a contrast preparation module where you manipulate the magnetization ahead of imaging, and then having manipulated the magnetization of your subject ahead of time, you then take a kind of snapshot, or use the imaging techniques to take a kind of snapshot of the contrast that you've prepared, and you end up with, you've got a lot more scope for controlling the image contrast this way. So let's take a look at something called inversion recovery. Okay, so right at the beginning we talked about having this magnetization that was aligned along the magnetic field, and we could apply an RF pulse to flip it to some angle. So what if we flip it with a 180-degree pulse to start with? Then the magnetization ends up upside down. It started at 1, and now we're going to flip it all the way over to, say, -1. And then it recovers by T1 longitudinal relaxation along this curve, and if we, depending on how much time we wait, 1 second, 2 seconds, 3 seconds, 4 seconds, and after about 5 seconds, if it's a T1 of a second, it's almost back to where it started. But if we were to image it, if we did this 180-degree pulse, and then we were to image it at some point along here, the magnetization, the signal we'd see in the image would be much different from if we just started with it fully relaxed. Okay, but why is this useful? Well, it's useful because each tissue typically has a different T1. Okay, because the T1 is very much dependent on the environment of the tissue, the local environment of the tissue. So, for example, if we consider like white matter here has at 3 Tesla has a T1 of something like 800 milliseconds, and grey matter is something like 1.3 seconds. So if we do this inversion recovery trick, we do this 180-degree pulse, flip them both over, and then wait some time, the grey matter, the white matter and grey matter have quite different signal levels depending on how long we wait, and you develop a contrast that looks like this blue curve here. So if we choose to then image somewhere up here, we get quite a good grey contrast, white contrast within our image. So if we do the inversion pulse and wait something like 700 milliseconds, which puts us somewhere around this peak value here, and then do our imaging sequence, we should see nice grey matter, white matter contrast. Okay. In practice, we use this sequence called an MP-RAGE, and so we take all up, we have this 180-degree pulse, we wait this typical 700 millisecond time, and then we do a whole lot of little imaging sequences where rather than we just take little nibbles out of magnetization as we go for each one of these, and we acquire a whole lot of these for each inversion, so typically several hundred. So typically this is a 3D sequence, so we'll do all the slice direction image lines, and then we'll repeat this for each Y line. So the whole thing takes about 5 minutes, but you end up with rather exquisite grey matter, white matter contrast. Okay, and this is a mainstay of the of anatomical imaging for neuroimaging, this MP-RAGE sequence. Okay, so the scan times are typically about 5-6 minutes, sometimes 10 minutes if you need higher resolution. There's some variations on this. So typical resolutions would be like about 1 millimeter. Some variations on this is there's a multi-echo MP-RAGE where you can acquire different TEs during each module. And recently we've been using an MP2 RAGE sequence which requires 2 different TIs, which has possibly some advantages because it's supposed to be able to make spatial maps of T1 and T2 throughout your subject. So that has basically 2 different TIs like that. And this is almost all the imaging protocols involve some kind of anatomical imaging, and typically they'll include an MP-RAGE or an MP2 RAGE scan. Okay, another imaging sequence that is based on inversion recovery is a FLAIR sequence. In this case, this isn't so much for grey matter and white matter contrast, it's more about nulling the CSF. And so we basically have CSF is liquid. Liquids usually have a long T1. So we basically choose a time such that after inversion we wait for the CSF signals pass through the null point and then make our image, and we still get a pretty good a good level of signal from the brain tissue itself. So this is basically a standard FSE or TSE imaging sequence with an inversion recovery stuck on the front, basically, and you can control you can basically remove the effects of CSF in these images. Okay, and so then I just wanted to come back and recap on the EPI scan and talk about its contrast momentarily. As I said before, this scan basically acquires the entire image in a single shot. We can do accelerated methods and get something between, at 3 Tesla, it's pretty typical to get anything from 2 to 3 millimeter resolution. That's limited by the gradient strength. And we can apply, and that's using parallel imaging methods too. And one consequence of the way that it reads out, because it goes to the edge of K space and then zigzags back, is that it crosses the center of K space only quite a long time after we initially do this initial excitation. So often it takes about anything from about 15, 20, 30 milliseconds to get to this middle of K space. And it turns out that the image contrast is largely dominated by the center of the data you acquire at the center of K space. So the contrast you perceive in your image, if you remember the picture of Abraham Lincoln earlier, is very much dominated by what's happening when you with the signal when you get to the center of K space. And so if we're passing through here at about 20 or 30 milliseconds, that means we have a very strong T2 star weighting, because the signals which have the spins which experience a very uniform field are still quite strong. The ones which experience a lot of variation in field have been dephased and become quite dark. And that's exactly the effect that we need for bold contrast. So it turns out the EPI sequence is pretty much ideal for making bold images, because we typically want to be collecting data at around 25, 30 milliseconds for to get the ideal bold contrast, and so that's what we aim to do with that. Okay, so just to wrap up, I just wanted to make a couple of comments that in terms of safety, in terms of the patient safety, there's really two things to think about. One is the specific absorption rate, which is the amount of RF energy which is deposited into the subject during imaging. And this is related to the kind of how many RF pulses you're using and how strong they are. So EPI scans typically don't use very much because they just have that one excitation pulse and then a lot of gradients. Some imaging methods such as TSE and FSE have quite high because they're using a lot of 180-degree pulses. Some multiband methods, because they have that combined pulse which excites multiple slices simultaneously, each of those bands basically acts like a completely separate RF pulse, so they have pretty high SAR as well. So typically the scanner will warn you. It monitors how much SAR has been applied to the subject, and it'll warn you and ask you to derate your sequence and maybe reduce the flip angle if you run into problems with this. The other thing to consider is peripheral nerve stimulation, and this is caused by the imaging gradients themselves, because when you think about those imaging gradients, we've got these magnetic fields that we're turning on and off, and when they switch, they basically induce currents because you have a conductor in the magnet, and it would basically introducing electric fields in the tissue, and this can cause sensations in peripheral nerves of the body. And so it can be either, sometimes a lot of the time you don't notice it at all. Sometimes you can feel a sort of tickling sensation. Sometimes it's painful. So this needs to be, you need to watch your subjects, particularly for sequences that switch the gradients very rapidly, such as echoplanar imaging. Okay, there's a whole lot of other stuff, but I think we're nearly out of time. We could talk about, but maybe some of these things will come up later in the course. Anyway, I'm going to wrap it up at that point. Any questions? Okay.